Hi, welcome to another video in my series on entanglement. Tonight I will demonstrate the phenomenon in a Jupyter notebook using QuTiP, the quantum toolbox in Python. Entanglement is a way for particles, or quantum bits of information, to communicate their state to one another. The quantum internet will need repeaters to transmit information over long distances, and these repeaters will rely on entanglement to do so. The first notable discussion of entanglement was the 1993 paper in Physical Review Letters entitled Teleporting an Unknown Quantum State, and it is the basis of the code I have written for you. The Jupyter Notebook simulates the physical process described in that paper. The first part of the notebook covers teleportation, and the second part simulates an extension of the teleportation idea to transmit a quantum bit of information using a repeater. In both parts, the initial state and the received state are visualized on the block sphere in order to verify that they match. In this story, Alice is teleporting an unknown quantum state to Bob. Here is the notebook. In cell 2, there is the function for extracting the block sphere coordinates from the density matrices and displaying the points on the block sphere. Cell 3 sets up and executes Alice's measurement in the Bell basis. The function measurement statistics accepts a list of operators, one for each possible outcome, and returns two parallel arrays, one for the new states formed by measurement collapse, and one for their corresponding probabilities. The cell iterates through the four possible outcomes. Alice communicates her measurement results to Bob at the speed of light, and Bob uses this data to select a quantum operation to perform on his particle. The next to last statement is a unitary transformation of the density matrix corresponding to Bob's operation. This reconstructs the data. The last statement visualizes the results before and after, as shown in the next cell. As you can see, they match. If you download the notebook from my GitHub page and run it, you will be able to scroll through the four outcomes. The second part of the notebook covers entanglement swapping, the key repeater technology for the quantum internet. This is an extension of the teleportation paradigm. The diagram in this cell illustrates the process. There is a transmitter, a repeater, and a receiver. The transmitter has the data qubit and shares two linked qubits with the repeater, the second of which is also shared with the receiver. The receiver has a qubit for the received data. Altogether, there are 5 quantum bits, or qubits: the data qubit, 3 linked qubits, and the received qubit. Cell 4 sets the state of the data qubit, entangles qubits 1 and 2, and also entangles qubits 3 and 4. The tensor function collects the qubits into a 5-qubit multipartite state. In cell 5, the repeater measures qubits 2 and 3 in the Bell basis, and then does the same for qubits 0 and 1. There are 4 possible outcomes for each measurement, so there are 16 possible outcomes altogether. The measurement function differs from the previous function, measurement statistics, in that it is non-deterministic. It returns a single measurement result by chance, selected according to the rules of quantum mechanics. Each time the cell is executed, the function can return a different result. No matter which of the 16 possible outcomes occurs, application of the proper gate, that is, the proper unitary transformation, will reconstruct the original qubit at the receiving station. The third to the last statement in this cell is the unitary transformation. The final cell shows a visualization that verifies that the received qubit matches what was transmitted.